Welcome to The Explainer, where we take big, complex topics and make them crystal clear.
Have you ever stopped to wonder, how does anything stay perfectly still? I mean, how do massive bridges just stand there? And how can you lean a ladder against a wall without it slipping? Well, today we're diving into the answer. It's all about a fundamental physics principle called the equilibrium of forces. It's basically the hidden science holding our entire world together. So here's our game plan. We'll start with what equilibrium even is, then get into something called the principle of moments. After that, we'll walk through a couple of classic examples, hit some practice questions, and even tackle some exam-style problems to put it all together. Let's jump in. All right, first things first. What do physicists actually mean when they say an object is in equilibrium? It's a word we kind of throw around, but in physics, it has a very, very precise meaning. At its core, it's a state of perfect balance. But here's the key thing. It doesn't just mean something is standing still. That's one type of equilibrium, for sure. But an object could also be moving at a totally steady speed in a straight line. The real secret is that there's no change in its motion. No speeding up, no slowing down, and definitely no spinning. And for any object to be in the state of perfect balance, it has to follow two crucial conditions. Think of these as the two golden rules of stability. Seriously, if you break even one of these, that object is either going to start moving or it's going to start spinning. No exceptions. So let's look at that first condition. A really cool way to visualize it is with vectors. If you take all the forces acting on an object and draw them out one after another, head to tail, they have to form a perfect closed loop. You end up exactly where you started, just like you see here. If there was any gap left over, well, that gap would be a resultant force, and that would mean your object is about to accelerate. Okay, so that's rule number one, no net force. But what about rule number two? Well, that one is all about turning, and it brings in a concept that physicists call a moment. Now, don't let the word moment throw you off. It's really just the technical term for a turning force. Think about it. When you use a wrench to tighten a bolt, or when you push a door open, you're creating a moment. You're applying a force at a distance from a pivot point, the bolt or the door hinge. And you know this from experience, right? The longer the wrench handle, the easier it is to turn the bolt. That's because you're creating a bigger moment.
And this idea is so important, it's got its own name, the principle of moments. And honestly, this is the key to solving pretty much any balance problem. All it says is this: for an object to not spin, all the turning forces trying to go clockwise must be perfectly canceled out by all the turning forces trying to go anti-clockwise. It's like a cosmic tug-of-war, and for equilibrium, it has to be a perfect tie.
Okay, enough theory. Let's actually put this principle into practice with a classic example from the textbook. This is where the rubber meets the road. So, here's our setup. We've got a simple rod. It's called light, which is just physics speak for let's ignore its weight to keep things simple. It's balanced right on a pivot. And as you can see, there are a few weights hanging off it, all trying to make it spin one way or another. So, here's our puzzle. What is the exact value of that unknown force F that we need to apply to keep this thing perfectly, beautifully level? All right, let's break this down. First step, let's sort our forces into two teams, team clockwise and team anti-clockwise. Looking from the pivot, that 2.5 Newton force wants to turn it anti-clockwise. The 1.2 Newton force and our mystery force F, they're trying to turn it clockwise. Then we calculate the moment for each one, which is just the force times its distance from the pivot. Okay, now for the magic step. The principle of moments says team clockwise has to equal team anti-clockwise. So we just write that as an equation. And look at that, we've got a pretty simple algebra problem. All we have to do now is solve for F. And when you crunch the numbers, bam! The force we need is exactly 2.0 newtons. It's that precise. Any more, and the rod would tip clockwise. Any less, and it goes the other way. 2.0 is the magic number for perfect balance. All right, that was pretty cool. Now let's up the difficulty a bit with another worked example. This one's got forces acting at angles, which means we're going to lean really heavily on that first condition of equilibrium we talked about.
So here we have a rod just hanging out in equilibrium, held in place by three forces. We know its weight is 50 newtons, pulling down from the center. We know there's another 29 Newton force pulling at a 60-degree angle. But that third force over there, force X, that's a complete unknown.
So here's the key to solving this. Because the rod is in equilibrium, we know the net force must be zero. And that means if we draw the three force vectors head to tail, they have to form a closed triangle. It's the law.
So by either drawing this triangle out to scale or by using a little bit of trigonometry, we can figure out the properties of that missing third side. And when we do that, we find that force X must have a magnitude of 29 newtons and act at 60 degrees to the horizontal. It's the only way to close the loop and keep everything perfectly balanced.
Okay, you've seen the principles in action. Now it's your turn. Let's run through a couple of quick-fire questions to see if it's all sinking in. You ready?
First up, another balance rod. Take a second. How would you find the force F needed to keep this one level? Yep, you got it. You'd use the principle of moments. Tally up all the clockwise moments, set them equal to the anti-clockwise moments, and solve for F.
Okay, next question. This one goes back to that problem with the angled forces. It's asking you to prove that all the vertical forces cancel out and all the horizontal forces cancel out. This is really just another way of confirming that first rule of equilibrium, by breaking the angled forces into their up, down, and left-right components.
All right, let's level up one more time and apply these same two rules to some typical exam problems. It's the same physics, just in a new context.
Okay, picture this. A wooden plank is resting on two rocks. The rocks are pushing up with forces P and Q, and the plank's own weight, R, is pulling it down. For it to just sit there in equilibrium, how are those three forces related? Well, all the forces pushing up have to exactly match the total force pulling down. So P plus Q must equal R. That's a direct application of our first golden rule. The net force has to be zero.
Here's another classic problem. You've got a rod suspended, a couple of weights are on it. Your job is to find the one perfect spot to hang a 6.0 Newton weight to balance the whole system.
And if you apply the principle of moments, balancing all the clockwise turning effects against the anti-clockwise ones, you'll find that sweet spot is exactly 17 centimeters from end X.
And for our final question, let's bring it all home. After everything we've looked at, what are the two fundamental conditions for any object to be in equilibrium?
And here they are one last time. First, the resultant force on the object must be zero, no overall push or pull. And second, the total clockwise moment about any point must equal the total anti-clockwise moment, no overall twist. These two rules are the master key to it all.
And here's the coolest part. These principles aren't just in textbooks, they are everywhere you look. They're what's keeping a book resting on a table, a ladder leaning against a wall, and the very architecture of a skyscraper standing strong. Our world is literally built on objects in perfect calculated balance. Now that you know the rules, what hidden examples can you spot around you? Thanks for watching.